That was, I think, number 30. So I gave you an even problem. I think your homeworks were all the odds out of that section. So I just gave you one of the even ones. Let's take a look at it. I'm not sure how this is going to turn out here. Did I start recording? Yeah. Oh, man. Why can't I rotate this? Why can't I do this? There we go. Whoa. All right, so here we go. So there's the original function, 5x cubed minus 3x to the 5th power. Did I write it down wrong? Oh, shoot, I wrote it down wrong? No, I didn't. Okay. I'm not going to be able to show them both, barely. Okay, so the derivative, we have to take derivative of this. So a derivative of that one is 15x squared. And derivative of that one is minus 15x to the 4th, right? So there's your derivative. And now you need to set that derivative equal to 0. So you set it equal to 0 and then just pull a GCF out of here. So pull 15x squared out. And that leaves you with a 1 here, and this leaves you with an x squared here. And then this is a difference of squares, which factors, and then you set each of these equal to 0, and you get these 3 solutions. Then once you have those 3 solutions, you draw a number line. You put your solution 0, negative 1, 1. That breaks the number line up into 4 regions. And you pick a test point in each region. So negative 2, negative 1/2, 1/2, and 2 is what I picked. And you take those and plug those into the derivative. So I went and I didn't use this form of the derivative. I actually went down to where I had factored it right there. I rewrote it right here. And then I just plugged in like negative 2 into this. This is always going to be positive no matter what. No matter whatever plug in for x. So that, all of these are positive. And then when I plug in negative 2 here, I get 1 minus negative 2. That's 1 plus 2, so I get a positive. Plug negative 2 in here, we get a negative. So if we multiply these, we get negative. And I did that for each of the points. So I got negative, positive, positive, negative. So it didn't switch there, which means that my graph went, my function goes down, then up, up, then down. So you have, well, it's increasing between negative 1 and 1, and it's decreasing from negative infinity to negative 1, and also from 1 to infinity. We have a local minimum at negative 1. We have a local maximum at positive 1, and you have to plug those values into the original function. So you plug 1 into the original function, you should get 2, and you plug negative 1 to the original function, you should get negative 2. So that's it. I saw a lot of different things when I was picking them out. I saw lots of variations of this. So I'll grade them, we'll see how they go. Okay, we continue. All right, so what we learned last time is that the first derivative of a function tells us all about where a function is going up and where it's going down. And from that, we can find local maximums, local minimums, right? And what we were looking for is, anywhere we went, our function goes up and down, we should have a local max there. Anywhere we go down then up, we should have a local minimum. Now we move on and talk about something that has to do with the second derivative. So the first derivative tells us up and down. What does the second derivative tell us about a function? And what it determines is what's called the concavity of a function. And here's the definition. Okay, I can read through this. This is exactly like this, what we had for the first derivative. First derivative, positive means up, negative means down. Same exact concept, except we look at the second derivative. If the second derivative is positive on some interval, then the function, the original function, is what we call concave up, or concave upward. And concave upward means that the graph must look something like that, okay? And then if the second derivative is negative, then we will have our function must look concave down. So positive is like a smile, negative is like a frown, right? So that's it. That's what the second derivative tells us. It just gives us a little bit more in terms of the shape of the graph. Now, anywhere where we have a change in concavity, so when we have, remember, if we did a number line, you know, we had, let's say, like the quiz problem, anywhere our function went down then up, right? It was a change in the first derivative, right? The first derivative was negative then positive. Over here, the first derivative was positive then negative. You know what? Yeah, it was positive then negative. So if we have a change in the first derivative, it tells us we're at a local minimum or a local max. But what does a change in sign of the second derivative tell us? Well, it tells us that we are at what's called an inflection point, all right? An inflection point. And the best way to see what an inflection point looks like is to just look at the graph of a function, and you will, I think it'll become easier to understand. Okay, so second derivative has nothing to do with up and down, all right? Nothing at all. Just has to do with the shape of the graph. So let me show you some concave up and concave down, and then I'll show you an inflection point. So take a look at this function right here. As I start to move to the left, from the left to the right, the red line, okay, the red line that I'm graphing is the derivative, the first derivative. So we are increasing here, aren't we? But look at the shape of the graph here. Do you see that the shape of the graph, this looks like part of a frown? You'll see that? So I'm gonna keep moving and watch where it switches. So it's red right now. Watch where it switches to green. You see that right there? Let me just move all the way across. Get off the screen. So look, from over here to about right here, doesn't our graph appear to be part of a frown? And then there's this switch, and like somewhere around right here, this starts to look like part of a smile, right? And then it switches again. Now we look like we're part of a frown, and then right in here, we're part of a smile again. So this point, this place where we have that switch from a frown to a smile, here a smile to a frown, here a frown to a smile, those are our inflection points. Okay, so it's anywhere where part of a smile would meet a frown or the other way around. All right? Understand? Now, also, pay attention to something. The second derivative and first derivative are very different, right? Because if I'm talking about the first derivative, do you agree that to the left of this, my first derivative is positive, right? To the right of this, my first derivative is negative until when? I'm talking about the first derivative right now. Negative, 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 negative. Right here, what's my first derivative? What does it look like? 0, but then as soon as I get past that, negative, 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 until I get down to here, right? So it looks like here is where my derivative would become positive again. So do you see there's a big difference between the two? What's happening with the first derivative and second derivative, they don't coincide, all right? Make sense? Okay. Let's see what else we've got here now. So we have what's called the second derivative test. I don't use this much, all right? But it's in the book, and I know that a lot of other professors do use this second derivative test, so I just want you to be aware of it, but you really won't see me use it that much. Here's what it says. The second derivative test says, suppose that the second derivative is continuous near C. In other words, when you take the second derivative of a function, it's well defined. Okay, it doesn't have, there's no division by zero or anything like that. So you've got this nice continuous function when you take the second derivative. So it says if your first derivative is 0 at some point and the second derivative is positive, then you have to be at a local minimum. Let's see why that's true. I'm going to show you with the picture. Okay, so let's say we have some point, all right, on our graph. And what if I tell you that at that point the first derivative is 0? Then you know that it has a flat tangent line here, right? That's all you know? But what if I then tell you the second derivative is positive? That would mean it has to look like what? A concave up, right? So if the second derivative is positive, then your graph has got to look something like that there, right? And the only way that that would happen is if you were at a local minimum. Does that make sense? Now, another thing we could look at is what if you have the opposite happening? Oops, let me take these all out of here. What if you go to a point, right? The first derivative is 0. This time the second derivative is negative. Then you know that you are at a local maximum. Okay, so it's a nice test, right? It's a nice test. But it requires that you calculate the second derivative. You have to calculate that, right? And sometimes the second derivative can be pretty complicated. So we can find local maximums and minimums, can't we? We can already do that? That was what the quiz was about. So you just set up a table, you look for up, down, or down, up. So we can do it. This is just kind of a plan B if we need it, all right? All right, so let's continue here. Yeah, that's it. So let's do some examples. So we are officially down to our last, we have 7 class meetings left, including today. So we have 4 weeks left, and we have a test that we're supposed to be having pretty soon. May 2nd. May 2nd, yeah. I've thought about moving it, but I'm not sure what we're going to do. So you know what? Let's do the quiz problem. How about that? Let's do the quiz problem, but for the quiz problem, let's talk about the concavity, all right? So the original function was f of x was 5x cubed minus 3x to the 5th. So part A, find where this function was going up, where this function is going down. Part B, find the local max and min. Part C, I want us to find where the function is concave up and concave down. So the way that I'm going to do that is, you know how I used arrows here? I'm just going to use little like concave up and concave down, all right? So that means find where it's concave up and down. And then part D is to find any inflection points. Okay, so part A and B, we're done on the quiz, right? So now let's do part C. So for part C, we need to take a look at the second derivative. So our first derivative, we've calculated that to be 15x squared minus 15x to the 4th, right? And now we need to take the derivative of that again. So the derivative of that would be 30x minus 60x cubed. This second derivative will tell us everything we need to know about where our function looks like a smile and a frown, all right? But how do we do it? What's that? Set it equal to 0, and then do a number line and do test points, just like you did with the first derivative. We're going to do the exact same process, but we're working with the second derivative instead of the first, all right? So there's really not a whole lot of new stuff other than the fact that we're working with the second derivative, and our results tell us something else, all right? So I'm going to take my second derivative. I'm going to set it equal to 0. So I take 30x minus 60x cubed. I set it equal to 0. I can factor out a 30x. I'm left with 1 minus 2x squared, is that right? Okay. And then I set these factors equal to 0. So when I set that to 0, I just get one answer. And then I have to set that to 0. And you have different options here in terms of how you can solve this. I'm just going to move the 2x squared over, and then I'm going to divide by 2. And then I'm going to take the square root on both sides. So when I take the square root on both sides, I will get plus or minus, right, because you're taking the square root. Square root of 1/2 equals x. And there's all sorts of different ways we could write square root of 1/2. We could go 1 over root 2. We could do root 2 over root 2 if we rationalize it. I'm just going to leave it like that. All right? Now, we're also supposed to look and see anywhere where the second derivative doesn't exist. And we were supposed to do that for the, on the quiz, when we took the first derivative. We were supposed to look at where it's 0 and where it doesn't exist. But the fact that it was a polynomial, I didn't even consider it. But as we move on, the problems get more complicated, like the functions get more complicated. We always want to take a look at this and whether or not it doesn't exist. But it's fine, right? This is a nice polynomial again, so I'm just going to keep going. So number line now. So here comes my number line. And I'm going to have 3 points. Here's 0. Here's square root of 1/2. And here is negative square root of 1/2. Right? And now you're going to break up your number line into 3, how many regions are we going to get from that? 4 regions. And that means we're going to have 4 test points. And we're going to take those test points and plug them into the second derivative, right? So we have to pick something here, 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 and here. So you need to make sure you get numbers that lie in those regions. So if you need to get on your calculator and figure out what this is, then you go do that. I think it's like 0.707 or something like that. So this is positive 0.707. This is negative 0.707. So anything over there, what do you say, negative 1? That'd work, right? And then something here. Negative 1/2 would work. And then positive 1/2. And then over here, 1 again. So, and now we're taking those and plugging those into the second derivative, because the second derivative is going to tell us whether or not we're concave up or down. So let me do it right there. I think I'll work with this one. That's fine. So I need to find out what is f double prime of negative 1, f double prime of negative 1/2, f double prime of positive 1/2, and f double prime of 1. Forgot to mute my phone. All right, so negative 1 in here, what do we get? Negative 30, right? Yep. And then you're going to have negative 1 cubed is still negative 1, and then times 60, and then subtract it. So that's going to be a plus, isn't it? So negative 30 plus 60, it's a positive number. That's all I care about, right? Now let's do 1/2. So, or sorry, negative 1/2. We go negative 1/2 in here. Let's go ahead and do it. It's negative 15, right? Minus 60 times, now what's negative 1/2 times negative 1/2 times negative 1/2? Negative 1/8, like that. Okay, and so what would happen if we put these together here? We're going to have negative 15, it'll turn out plus 60 over 8. Right? This turns out to be a negative number. Okay, you can check it yourself, do it on your calculator. This is a negative number. All right? And then we do the next two. I'm just going to give you what they are, all right? I'm not going to go through the work. This one will be positive, and this one will be negative again. All right? So, now what does that tell us? That tells us that over here, to the left of this, our original function is concave up, smiling. So I'm going to do this. You know how I was doing like up arrow, down arrow? Now I'm just going to do concave up like that. And then here it's concave down. And then it's concave up. And then it's concave down. Right? And when I'm saying concave up, I'm referring to the original function as concave up, right? The original function is concave down. So now let's answer the questions. Part C. Part C says where is the function concave up? Where is it concave down? So f is concave up where? Negative infinity. It's a negative 1. Union 0 to root 1/2, right? So that was... yeah, it should not be negative 1. It should be negative root 1/2, yeah. So I mentioned this when we were doing first derivative, that I usually circle my test points so that I don't accidentally put them into my intervals. And I also put X's here where my test points are. I don't put dots, and that's just out of habit. All right, let's keep going. Where is it concave down? So this time it's going to be from negative root 1/2 to 0, and then union from root 1/2 to infinity. So is everyone comfortable with this? I mean, really, there's nothing new here, right? Do you agree with that, other than what it's telling us? Part D is inflection points. So this is where there's a slight difference. With the first derivative, we're looking for local max and min right now, right? But with the second derivative, we don't care if it's going from smile to frown or frown to smile. We don't care. As long as it's changing, it qualifies as an inflection point. So we actually have an inflection point here, an inflection point here, and an inflection point here. We have 3 inflection points. So we have inflection points at x equals negative root 1/2, and then at 0 and at root 1/2. Yeah, so now the question is, do we need to plug these into the original function? We don't have to, because look, with the first derivative, we're actually asking for the local max and min, right? We want to know how high that function was and how low that function was. Here, we just want to know where the switch in concavity happens. We don't necessarily need to know the y value. Now, if you want to, you can plug those in, all right? But if you leave them just like that, that's also okay. Understand? So I'm just going to leave them. All right, that's it.
We're going to do the graph.
The graph of what?
First derivative and then the second derivative, and then you connect them and you do the whole.
That's the next section. So the next section is, now let's use all of this together to graph. Yeah. So we're headed there. We're very close to that. Okay, now a little bit about the inflection point. You might wonder why an inflection point might be important to know, right? I mean, like, what's the big deal? I mean, it would be nice to know where your local maxes and mins are, but where would an inflection point come into play? So I'll just give you an example of kind of a classic problem. This is like from a business class. Let's say that they have some function that, I don't know, maybe this is time here, and maybe this is their profit, okay? So their profit as a function of time. And so maybe their function looks like this. All right? So what you will notice about this profit function, let's call it P of t, because it's profit as a function of time, right? Here's like the input and there's the output. What can you tell me about the first derivative of this thing? Is it positive or negative? It looks like it's always positive, right? Now we're not going to look to the left here because time isn't negative, right? So you could say, okay, our profit function is, the derivative is positive, which means our profit is always growing, right? Which you can tell it is. But what about the inflection point? Do you see the point where it goes from like a smile to a frown or a frown to a smile? It's somewhere in here, right? Somewhere about in here, and we'll just kind of eyeball it. Is that good? Okay, so there. Why is that an important point for us? What's that? It's slowing down. So if we take a look at the tangent line, okay, let's just take a look at the tangent line. Okay, in the beginning, look at the slope here, right? We are increasing, right? And the slope is positive, right? So that's great. And then we get to this point. Once we get past that point, we still have positive, right? But it's not going to be as steep. You see that? So we're growing, but not as fast, right? So this point in a business class, this point is very important. This is actually has a name. It's called the point of diminishing return. The point of diminishing return. So what's happening is, yes, you're still bringing in money, but not as fast as you were. And maybe, time may not be a good example of this. Maybe it is time. Yeah, time might be a good one. So as a business, I might look at this and say, okay, we looked at the year, we looked at the last year, and it was somewhere around here we had this point of diminishing return, right? And we go back and we look, what happened? What happened back then? And that's when we hired Jace. So, I have to pick on somebody, right? Okay. Yeah. So, right? So no, you go back and look at, oh, that's when we brought in the new machinery or something, right? It's like something happened that is making us not as we're still profiting, but not as much. So you might want to look at that and see what happened, right? Does that make sense? So that right there is an inflection point. For a calculus student, it's an inflection point. From a business perspective, it's the point of diminishing return. And you can do this for anything. You don't have to do business. You can do something else. This can be, time, and this could be a force, or this could be time, and this could be, you measuring the temperature in a chemical reaction or something. It could be anything. That inflection point means something. Yes?
So in business calculus, so they have like a faster way of like finding that point?
No.
Or they do the same?
No, in a business calculus class, the main difference between a business calculus class and this class is, first of all, they don't spend a lot of time on limits. They do it, but they don't do a whole lot of it. And then they stay completely away from trig functions. Like they don't touch sine, cosine, tangent. They don't do any inverse trig functions. And so their differentiation, when they take derivatives, they get the shortcuts earlier in the semester, and then the functions they look at are just easier to deal with. They're mostly always polynomials and very nice, and yeah. There is a night and day difference between the two classes. Okay. Yeah, so now I think we should do another example. Man, I looked straight into the projector just a second ago, and it's like blinded me. Whoa. So let's do the same instructions on this one. We're going to do the whole thing. We're going to do, where's this function increasing and decreasing? Where is it, where are the local max and mins? We're going to do, where's it concave up and down, and where are the inflection points? All right? So here we go. I think it's time to do something a little bit uglier. So let's do f of x equals square root of x squared plus x minus x. That's one of the uglier functions we've looked at, I think. Would you agree? So if we were to have walked into this class on day one and were asked to give some indication of where this function has highest and lowest points, that would be a challenge, wouldn't it? Okay, so first thing I'd like us to consider is something we haven't really focused too much on, because all the functions we really have done have been polynomials, but we need to talk about the domain of this function before we start, because we need to see what's in play and what's not in play in terms of x. So let's just try and see if we can figure out the domain. Okay, so what can you tell me, what would cause a problem for this function? If what's underneath that root was negative, right? So here's what we need. We need, for this thing to make any sense, we need x squared plus x to be greater than or equal to 0. So we need the radicand, the thing under the radical, to always stay positive, or it could be 0. It's okay to take the square root of 0, right? So this is what we need. This right here has a name. This is called a quadratic inequality. And there is an entire method on how you solve quadratic inequalities. There's a correct way to do it, and there's an incorrect way to do it. So the correct way to solve a quadratic inequality, and you may know this, hopefully you do. If you don't, here we go. The first step is to turn it into an equation. Okay, so you start off by first writing it as an equal sign. Even though it's an inequality, we write as an equals to start. And then you solve that equation. So let's solve it. Just factor an x out. So you get two answers, 0 and -1, right? Okay, so at 0 and -1, this thing, if I plug in 0 or -1 into this, right, I'm going to get 0. The question is, what do I need to plug in to make sure that it's greater than or equal to 0? So the next step to solve a quadratic inequality is you draw a little number line and you test points. This is weird because this is kind of what we've been doing, right? But this has nothing to do with what we've been doing. This is just how you solve quadratic inequalities. And now what you do is you pick test points and you plug those into that and you see if it's a thumbs up or down. So let's pick some test points like -2, -1/2, and 1. And let's just see what happens. So what happens if I plug 2 in here? Will that be true? Will 2 work? Did I mean? Yeah, I meant to say -2, sorry. I meant to write -2. -2 in here would give you 4, and then plus -2, so that would give you a 2. 2 is greater than or equal to 0, right? So that works. So anything over there works. Okay, what if you plug in -1/2? So plug it in, check it for yourself. It won't work. So nothing here works. And if you plug in 1 and plug it in there, it works. So that tells me that anything to the left of -1 and anything to the right of 0 works, right? So the domain of this function is everything over here, forever, everything over here, forever, and then what about -1 and 0? Do I include those or not?
Yes.
Yes. Because it's okay to equal 0, right? So my domain is -∞ to -1 bracket union 0 to infinity. Close. So we need to keep that in mind because when we're looking at where this function is going up and down, we're only allowed to look here, right? These two places. Okay. I didn't tell y'all about my welding. I think that's why that light really messed up my eyes. Did I tell you about my welding I was doing about a month or 2 ago? I'm not a big welder, but I can make metal stick if I need to. It's not pretty. All right. So I was welding in my garage and I had my little helmet on. It's one of those ones where it's anyone know anything about welding? Okay, so it's the ones that, I don't know what it's called, but like you can see through it, but as soon as you hit the arc, it like darkens. It wasn't working, but I didn't realize it until I had been like welding for a little while. And like for the next hour, I had this like bright light in my vision. I think I messed my eyes up. I really do. Because now I'm having trouble like reading things on my phone. So I need to go get it checked out. What are they going to do? Replace my eyes? I don't think so.
No, they have your atropine drop.
Yeah. I think it's too late now. I've waited too long.
Did you ever teach like algebra?
Did I ever teach algebra?
Yeah.
What do you mean?
Here,
Huh? Sure.
college algebra.
It's been a long time.
I wish I had you as a
Yeah, it was
teacher, 'cause
a
lot
long
of the
time ago.
stuff that like we review, like the teacher that I had, he told us like the hardest way to like do like simple stuff like this, like how to like solve equalities and stuff. I don't know.
No comment.
We didn't even see it this way. Like you said, like the sign will flip. Like we never like said it. Yeah.
Yeah,
it's
I don't know.
divided, but
Yeah. Yeah, well, I mean, yeah. Yeah. What could have been? All right. So now let's talk about where this thing goes up and down, right? So do you agree we're going to need, for up and down and concavity, right? We're going to need both derivatives. So let's just crank those out now. Yeah, so this derivative is going to kind of suck. All right. All right, so the derivative of square root of something is 1 over 2 square roots of that something, right? Times what? 2x plus 1, right? You have to take derivative of what's inside, right? Chain rule. So times 2x plus 1, and that needs to be in parentheses, right? And we're not done. All of that minus 1. All right, so I'm going to clean this up just a little bit. This is 2x plus 1 over this. That's it, right? That's our first derivative. We will need to set that equal to 0. But for now, let's just kind of let it sit here, and let's go ahead and get the second derivative now. All right, second derivative I think is going to be messy. So when I do my second derivative, well, this is going to be the easy part, right? Derivative of that's going to be 0, so I don't even have to worry about that. But this is going to require a quotient rule, right? So it's going to be derivative of the top, which is 2, times the bottom, right? What? Minus the derivative of the bottom. So what is the 2? What happens with the 2? It just comes with us, right? Okay, so just bring it with us now. Derivative of that is 1 over 2 roots of, I'm going to just do it this way. But then chain rule again, right? And that would be up here on top like this. So since we've already done that, right? We did that right there. I'm just going to put it right here. So that's the derivative of the bottom, except that we have that 2 that was out here. With me? Times what, though? Times the top. What's the top? 2x plus 1. And then all of this over the bottom squared. So I'm going to square the 2, it becomes a 4. And when I square the square root, it goes away. But I still need it in parentheses because that 4 will distribute through to each one. Okay. Any questions on that derivative? Not pretty, right? Not pretty. This is nice, though. Yeah. Did I upset Jace? I think I did. You okay? Okay. I was kidding. I was kidding. I know. So our second derivative did I tell you all about, sorry, I'll mute my microphone for this.
The only thing that annoys me is
Is what? Anti-vaxxers? Oh man, that's a long conversation, I think. Okay, so I'm putting this together now. That's a 4 in front of that root, and then over here, those two's canceled. These two are the same, aren't they? So that's going to be minus 2x plus 1 squared, but that's still over that root thing. And then that's still all over this. Yeah, there it is. Okay, in all its glory, there it is. Yeah, I'm going to work with it. We're going to work with it, but I think we've gotten it to a point where we can say, okay, we have the second derivative now, right? I mean, that's pretty okay. Yeah. So let's now, I'll write the first derivative over here, so we have them both. And 2x plus 1 over 2 root x squared plus x, and then minus 1. So there's my original function, the first derivative, and the second derivative. And now I get the pleasure of trying to figure out where this thing is going up and down. And my domain, remind me real quick, it was negative infinity to negative 1, 0 to infinity. Okay, so I'm only allowed to look there. All right, here we go. I'm trying to figure out where my original function is going up and where my original function is going down. So I take my first derivative and I set it equal to 0.
Your first one?
First. I said first, wrote double prime, didn't I? I think that welder might have gotten into my brain also. That bright light. So I'm taking my first derivative and setting it equal to 0. Yeah. I know you're tempted to move the 1 over. Yes? Okay. We can do that.
But if you do, you won't be able to go to the bottom.
Well, you could multiply both sides by the bottom at that point. So yeah, maybe we'll just stick with the algebra that seems a little easier to do here. So let's, we're going to have to get common denominators here anyway. So we'll get practice with that over there. So I'm going to move the 1 over. Right? And then I'm going to multiply both sides by the denominator. Okay? So 2x plus 1 and then 2 root x squared plus x. And this right here, we have to solve for x. And this equation has a special name. It's called the radical equation. And somewhere in college algebra, you were taught how to do this very difficultly. Yes? So does anyone recall how we can solve a radical equation? What the kind of technique is? Always try and get the radical, the square root by itself on one side, and then square both sides of the equation. Okay, so I'm going to, right, I think I'm going to avoid the division by 2 only because it'll create fractions. So I'm just going to square it right now. Okay, so I'm going to square the left side. And I'm going to square the right side. When I square the right side, that becomes 4. And then this one right here becomes that, right? Now the left side, I'm going to expand it, do 2x plus 1 times 2x plus 1. And when I do that, I'm going to get a quadratic on the left, aren't I? And I have a quadratic on the right, which means this is all going to turn out to be a quadratic when I'm all done. So this becomes 4x squared plus 4x plus 1. So that's what happens when I multiply that times itself, FOIL it out, collect like terms. We trust in that? Here to here? Yes, you do. I don't trust me, but... You don't trust me?
I don't trust anyone.
Okay. Ooh. Now what?
Can we do
Move them back.
It's a quadratic, right? I mean, just how do we solve quadratic equations? Just move everything to one side, right? Okay, so let's move everything to one side. These go away, that's nice. And I think we get at the end here, oh, what do we get?
You get 1.
No, not 1, you get 1 equals what? You get 1 equals 0. Don't you?
Yeah.
What does that mean?
You messed up.
No, it doesn't mean we messed up. These cancel. At the end, you get 1 equals 0. So what does that mean? This is not true. Not what were we trying to do?
Where it equals 0.
We were trying to figure out where the derivative was equal to 0, right? And what have we concluded? When we try to set it equal to 0, we have
Does not exist.
no solution, right? There's no solution to this, all right? There's no solution to this equation. It's impossible for us to ever make this true, all right? So that means the derivative is never 0. Y'all buy that? You okay with that? So this tells us right now, f prime of x can never be 0.
And then
Well, that means whatever it's doing, it's always doing. Like it's either always going up or always going down. Does that make sense, everyone? Okay, I think this might be the first time we've ever run into this. We've always been able to draw a number line and do test points, right? This is the first time where we don't have any test points to draw. Okay? So yes? You sure? Okay. So right now we have no test points. So what I'm going to do is I'm still going to draw a number line, okay? But I don't have any solutions from this. So what I'm going to do, I'm going to go back to my domain. We know that there's no graph in here, right? Agreed? There's a black region of my graph that I don't even need to look at. I don't have any points from here to put here to break this up. And I don't have any points to put over here to break this up to do test points, right? So what I'm going to do is I'm just going to pick a test point in each region, and I'm going to see what's happening to the derivative in each of these regions. All right? I'm just going to pick a point. So anything over here? 1. Okay, and then anything over here? -2. And these get plugged into the derivative. Okay, so let's just see what happens. What is f prime? What is f prime of -2? And what is f prime of 1? Okay, I'm going to use my f prime here. So let's do -2 into here. What would happen if I do -2 here? -4 plus 1 is -3 over 2 times the square root of, now -2 here and here would give us 4 minus 2 would give us 2. And then I'm supposed to do what with that? Subtract 1, right? Well, this is a negative number, isn't it?
Yeah.
Negative, take away 1, that's still negative. So it's a negative number. What does that tell me my function is doing over here? It's going down. Now, if we did not have separate intervals here, like if our domain was not split into 2, we would be done. Like you only have to test 1 point. But because there's 2 separate regions of domain, we have to go check the other one because it could be doing something different. So what happens when we plug 1 in? What do we get on top? 3 on top, right? Right, 1 in here. And then 2 root what? 1 plus 1 again, so that's root 2, and then we're subtracting 1. So is that negative or positive? That turns out to be positive. No, wait, hold on. It's negative still. Did you check that on your calculator? No? That should be, because that right there is 1.5, right? 3 divided by 2 is 1.5. And then I'm dividing that by 1. Oh, hold on. Yeah, hold on. Yeah, that's 1.41. So if I take 1.5 and divide it by 1.41, it's going to be bigger than 1. So no, this is positive. It is positive. So that's you on your calculator, right? So that means over here our function's going up. This is a good example that I picked. I'm throwing you right into the fire here, huh? Look, if we did polynomials like the first one we just did, right? I mean, polynomials are just too basic. Why have all these calculus tools if you're going to just do polynomials? You have to do something that's you give to a college algebra student, they're just going to throw up when they look at it. Okay, so let's draw some conclusions. where is my function? Oh, you have it, right? Okay, where is my function increasing? From 0 forever, right? From 0 to infinity. Where is my function decreasing? Negative infinity to -1. All right, be real careful here. Do I have any local maxes? And do I have any local minimums? This one's tricky. This one's tricky. All right, remember if you go down then up, it's a local minimum, right? But see, there's a big gap between these, aren't there? So this isn't really going down then up because there's this huge thing. So we can't, so we have a local minimum all in here, right? So imagine over here what this graph looks like. It's coming down, right? It's coming down, 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 down until it gets to -1, right? And at -1, that should be the lowest point over there, shouldn't it? Shouldn't that be like the lowest point on that side? So at -1, we should have a locally minimum point, meaning everything, when we look to the side that way, should be above. Does that make sense or not? So we should have a local minimum at f of -1, which should be, what happens when we plug -1 in there? So -1 squared is 1 plus -1, that's 0, right? And then we're doing minus -1, which is plus 1, so we just get 1 here, right? We have a local minimum of 1, and it happens at -1. And then what about a local maximum? Oh, wait a minute, hold on here. I think we have another local minimum, don't we? Because if you're over here, the graph starts taking off like that, right? And so if you come this way, it's coming down, and you should have a lowest point here when it comes into 0. So we actually have none. Let's put none here, okay? But we have a local minimum here and at 0. And what happens when you plug 0 into the function? You just get 0. Does that make sense or not?
Aren't the points supposed to go into the original function?
I did plug them into the original function.
Oh, okay.
Yeah, -1 went in here, and then 0 went in here. All right, do y'all want to look at it yet, or y'all want to work with the second derivative? Second? Second? Let's do the second, then we'll graph it, okay? And then we'll see how we did. The second derivative. I'm just going to erase all this, okay? Just going to erase all this. So my second derivative was what? 4 root x squared plus x oh yeah, that canceled. 4 that, right? Okay, so that was our second derivative. Now we need to set this equal to 0. So if I set this to 0, then the only way that can be 0 is if this is 0, right? Right?
The only way that can be 0 is
We got to get a common denominator before we can say that. Okay. But okay. We do have an issue though. We do have an issue. I'll get to it after we do this. This can only be 0 if the top is 0, right? And the top is all of this. So that can only be 0 if that top is 0. And now I get a common denominator on the left side. So I'm going to put this over 1, right? And I'm going to multiply the top and bottom of this by what? Root of x squared plus x. And root of x squared plus x. And when I do that, I think I do kind of like what happens here. Because these two roots go together, right? So I just get 4 x squared plus x's, and then minus this piece, 2x minus 1, or plus 1, that quantity squared, but then all over the common denominator of root x squared plus x. That all must equal 0. So there's my common denominator, right? And now that can only be 0 if the top is 0. So I set 4x squared plus x minus 2x plus 1 squared equal to 0. And that right there is already a quadratic, isn't it? And just expand it out. So we have 4x squared plus 4x minus 4x squared minus 4x minus 1. So I went ahead and expanded that out, right? This right here. That's 4x squared plus 4x plus 1. And then I distributed the minus 3 to each one of them. And then that must equal 0. And this time, we get the same thing, don't we? We get negative 1 equals 0. Which means that the second derivative is never 0. So we are back in the same position we were in just a little while ago, right? So there's no places where the second derivative is 0. However, do we have anywhere where the second derivative does not exist? At 0. Do you all see that? Here's my second derivative, right? Do you agree that if I plug 0 in, this thing's going to go crazy? And is 0 in my domain? It is in my domain, right? So we could say right now that we have a critical point at 0. But the thing is, it's an endpoint of the interval anyway. You know what I'm saying? Like, here's negative 1, here's 0. We know that we cannot be in here, right? So if that's a critical point, we would do a dotted line and then pick something on both sides. We're going to do that anyway. We're going to pick something over here, right? There's nothing to pick over here. So essentially what I'm saying is we're going to just do the same exact thing we just did a second ago, but go into the second derivative. So let's go negative 2 in there, and let's go 1 in there, and those are going to go into the second derivative. So f double prime of negative 2 and f double prime of 1. God. What's that? This was only the numerators, right? That was only the numerator, right? I'm just going to plug them in. It's not going to be too hard. If I plug in negative 2 right here, this gave me 2. So that was 4 root 2 minus, now what happens if I plug negative 2 in here? Negative 4 plus 1, negative 3, but squared. So 9 over, and what's this? Root 2, right? And that's all over this thing, right? Okay, do you agree that this is positive? Right? So this is going to be a positive number on the bottom. So 4 minus 9 over root 2. Or 4 root 2 minus 9 over root 2. Is it positive? I think it's negative. It's negative. Yeah, this is going to be negative on top if you put those two together. I'm just trusting you could just crank this out on your calculator. So this is going to be a negative on top and a positive on the bottom, which means we have a negative, right? Which means we are concave down, right? So this means over here we're concave down. And then when we plug in 1, let's see what we get when we plug 1 in. So we get 4 root 2 again, minus 1 into here. This is going to give us 3. That's going to give us 9 again, right? Over 1 there is root 2. It's the same thing, isn't it? So we get negative again. Which means we're concave down over here. No inflection points. So where is this thing concave down? You would say from negative infinity to negative 1, union, 0 to infinity.